Thank you so much for the introduction. Great to be here with you all today. So yeah, we're going to go across the ditch to New Zealand to introduce you to our field trial. So today I'm going to discuss kind of one aspect of our trial where we are using a catchment drainage approach within a working sheep farm to quantify the carbon removed from rock weathering. So for this, we're using aqueous phase methods to quantify the carbon removed by the amount of bicarbonate exported. So let me introduce you to our site. So it is a productive working sheep farm located at the very bottom of New Zealand in a place called Otahuti. And the general landscape here is it's a loose mantled downland, so it forms these kind of small drainage basins, and this is going to be the focus of a lot of what I discuss today. So, to provide some context for this, the soils are loess derived, and because of this, they form these dense frangipans in the subsoil. So this creates a significant drainage impediment, which makes these soils quite hard to manage within the winter. The water really perches and it's very difficult to manage these. So to overcome this limitation, an extensive mole and tile drainage system has been set up across the farm. So in these pictures here, you can see an example of a tile outlet and the small mole drainage channels within the soil. And we have made use of this artificial drainage system and these small drainage basins. So we have selected 2 drainage catchments within this farm, and you can see them on that image on the left, S1 and S2. And the black line in both of those shows the location of the tile drain. So that is what is draining the majority of the water out of these soils in winter. And to note here, S1 has an extensive mole drainage system, and you can see the location of those with those hashed lines in the right-hand image. Site 2 doesn't have mole drains for some reason, and that does create a little bit of a difference in the way these 2 catchments behave. But regardless, we are studying these catchments in tandem, although we can't necessarily say that S1 is a control for S2. So the beauty of using these catchments is that they act as a large lysimeter. So we can essentially monitor or capture all aspects of the water balance and measure the amount of water and the chemistry of the water that is being leached out of these catchments. So we measure the amount of rainfall and evapotranspiration from these. We can monitor changes in soil moisture. And importantly, we have these tile drain monitoring systems set up at the axis of both catchments. So this is where the water is draining out. So this monitoring system allows us to track the flow of water through the tile and to extract samples from it. We don't measure the amount of water going to deep drainage, but by monitoring all other aspects of the water balance, we can quantify this. So that means that we can quantify the total amount of drainage within these catchments and therefore the total amount of bicarbonate to understand carbon removed. So zooming in a little bit more to these tile drains, it's wet in Otahuti basically from April to October, and that's when the tile drains are really flowing to help drain these soils. So water samples are automatically retrieved during rainfall events, and there is continuous monitoring of the flow through these. So to the exciting stuff, we have selected basalt as our silicate rock of choice, and we source it from a quarry fairly close to our application site in the grand scheme of things, and are surface applying it at a rate of 50 tonnes per hectare. And so yeah, that's important to note. We're not incorporating this into the soil in any way, but the amount of bioturbation has been kind of more than we expected, and it does get mixed into the soil well. So bringing you to our project timeline, the sites were set up for monitoring by March 2024, and we then had a 1-year baseline monitoring period to help us understand what are the baseline rates of bicarbonate export from these two catchments. We then applied the first basalt to the site in March 2025 to S2, which was the larger catchment, the one without the moles in it. It's weathered for a year, and you can see that there. And then recently in March 2026, we applied another 50 tonnes per hectare to our site. So there's quite a lot of basalt on the pasture. So to quantify carbon dioxide removed, we are measuring bicarbonate export. We aren't measuring this directly, rather we're taking these water samples from our tile drain and measuring major cations and anions. We adjust for the charge on these based on differences in pH and temperature, and then determine that difference between cation and anion charge to be the amount of bicarbonate within the water. So we know the concentration of bicarbonate in our water samples, and we know the flow of water that was moving through the tile when that sample was extracted, allowing us to build this relationship between concentration and flow. We know the flow in the tile, as this is continuously monitored, and therefore, primarily I've been using LODEST, which creates this regression to plot load of bicarbonate over time, therefore allowing us to understand what is the cumulative loss of bicarbonate from these catchments over time. So, some preliminary results. Our 1-year baseline monitoring period showed us that despite the fact that S1 has these mole drains and that there might be some difference in management between these two parts of the farm, there were very similar rates of bicarbonate exported. And then since basalt went on, it says there March 2025 to present, but because the tile drains have only really just started flowing again after our second basalt application, it's really representative of the first 50 tonnes per hectare. But unfortunately, we're not yet seeing any signal of the basalt weathering in our water samples. And you will notice there that the loss has actually decreased, but that's been a result of it being drier since the basalt went on. Regardless of the lack of weathering signal, the bicarbonate exports are aligned to estimates from local river catchments. So we are seeing kind of similar rates there. But yeah, unfortunately, no signal of the basalt yet, but time will really tell. But one important thing is kind of trying to overcome the signal to noise issue, and using different statistical methodologies may help us with this. At the moment, the program we're using just fits a single regression to all of our data, but using a different software with more flexibility in these concentration discharge relationships may help us to get a better handle on actually understanding this data. So the future of the project, we are continuing to monitor our drainage water. So the 2026 leaching season's begun. So we're getting our first lot of water samples following our second basalt application, and hoping to see that increase in bicarbonate export there. To complement these drainage water approaches, we are also quantifying carbon removed in the solid phase using some mass balance approaches, and aiming to understand the wider scale implications of applying this much basalt to a sheep farm. So effects on pH, herbage nutrients, soil nutrients, and trace elements. And for that, you can see our poster for some preliminary results. And that picture there also shows how much kind of mixing is going on, thanks to the worms in our pasture. Thanks.